Okay, yeah, welcome to the Geophysical Seminar this week. Now it's my turn. I thought it would be fun to end the year with me telling you this story of a study I was involved in. I kind of stumbled into it, but it really became a special study for me. It was really intense, especially the first few months. I will show you how a rockslide-generated tsunami rang in a Greenland fjord, rang Earth for 9 days. And what I will present to you today is the combined work of many people. We were 68 co-authors from 45 institutions, a really very interdisciplinary, very international team with colleagues, of course, seismologists. We were mainly interested in the ringing part. There were landslide people, there were tsunami people, there were local geology people. All the disciplines came together to tell this story. So my contribution is a small one, and I really stand here representing everybody on the team. What I want to talk to you about today is not just the scientific story, what happened and how do we know this, but to give you a bit of a broader view of how the whole process of actually doing this work with 68 co-authors, how this went. So I will talk about how it started and how it ends, question mark, because it seems that it never really ends. It all started more than a year ago in September 17th. This is one day after the onset of the event that I will talk to you about all afternoon. And one of the first people to notice it was Rudi. Rudi is an old school seismologist. He works at the Black Forest Observatory in southern Germany. And he's the kind of seismologist that looks at his seismograms every day in the morning. So from the previous day's recording, he looks at his seismograms, just checking out what is in there. The 17th of September was a Sunday. So even on a Sunday, he checks his previous day's recordings. And he saw this signal here, which he found quite puzzling. And he wrote an email to his colleagues. It's in German, I will translate, titled, "What was this event yesterday on Saturday? Dear colleagues, what was this event? I see no earthquake that could fit, neither in the geophone catalog or at the NEIC. All of our sensors see it. STS1, STS2, STS6, these are seismometers, and a gravimeter saw the signal as well." Roughly at the same time, our Danish colleagues got reports of a local tsunami in eastern Greenland. Here we are at the very edge of eastern Greenland in the fjord system, and there were reports of a local tsunami by the police at Ellerø. Ellerø is this small island here in the fjord system in eastern Greenland. And this is a picture taken there in the aftermath, where you can see, for example, the containers a bit tumbling around. But what is most striking, certainly, is that there is this indication, this line separating the dark parts from the bright parts, where the dark parts are now water saturated because the water had run up this far. When I say this far, it's really just a few meters here, but you will see more extreme examples in a second. So what was this event that Rudi was so perplexed about, and that here apparently seems to be in connection with the local tsunami at Ellerø? It looks like this. This is the seismogram recorded at a nearby seismometer to the source of this event, where nearby is still more than 200 kilometers away, because it's a really remote area. And on the time axis, you have here days. So September 16th, around noon, the event started. And then we had this ringing for several days. We could see it up to 9 days, hence the title of our paper. And what really puzzled us is its monochromatic nature. It's a frequency of 10.88 millihertz, or roughly 92 seconds period. And it went on and on and on. And if you sonify it, you speed it up. Here, then it keeps going and keeps going. What it pops, these are earthquakes happening at the same time. Sounds like someone hits Earth with a big hammer and the phone went off. we had never seen anything like this before, right? I'm still fairly new to the seismology thing, but Rudi, he's now retired. He retired last month. He said he had never seen anything like it before, hence his email. And when we talked to colleagues worldwide, no one had ever seen anything like this. This was truly a new observation, and we didn't understand what it was at the very beginning. Here we're just a day after. So there was some interest in it, and a few emails were sent around, getting people together who are interested in working on it. And then very quickly, just a couple of days later, 4 days later, a MetaMost server was created to come and chat about this event and exchange our research and our ideas and what it could be. And here you see all the institutions that were then involved in the end, who came together to look at this. The entire communication went almost exclusively through chat on MetaMost. There were a few Zoom meetings between the core people, that's the main 4 authors of this paper. There were more Zoom meetings towards the end of finishing actually the manuscript. But almost everything was really, really open and uncoordinated. People just did their work, had some new results, put it in the chat. You went to sleep, and in the morning, people from the US had some comments on it, and it just went round and round and round. It was, yeah, especially the last 3 months or so of last year were really intense with this stuff. But in the end, we managed to get it done. So we started looking at some more features of this. Here you will see an animation of the signal propagating across Europe. All the dots are seismic stations. The color indicates the amplitude. And if we play it over time, you can see just a bunch of noise going on, more noise here in the sedimentary basin, for example. And then the event starts, you see some first waves, and then it just keeps going. The continuous excitation of these monochromatic waves with roughly 92-second period. And you can play this movie not as long as you want, but for several days. And it will just keep going and going and going. So we knew from this, you can already tell, okay, it must kind of come from the north. That's easy enough. So we tried to get a better location than just kind of from the north. And this was some stuff that I was involved in, where we tried to back project the energy. I took stations distributed all over the world, all stations I could get my hands on, all the data. In the end, I used roughly 1,000 stations, back projected the energy at 92 seconds. And in the beginning, here we're now at a slice before the onset of the event, it's just a big mess. But as we look over time, and then it starts, and then you see how exceptionally stable the source actually is. You also see that there's some challenges in actually locating the event because it's monochromatic. And that makes it challenging to pinpoint the exact location of where it comes from. But here also, we're now 2 days, 3 days in, and it starts to get less stable because, of course, the amplitudes decay, even though they decay very slowly. And we are almost the entire time able to see that energy is coming from there. So we had our eyes on the eastern Greenland fjord system just from the seismic data alone. We also had the reports of the local tsunami that happened at the same day. We didn't, at that time, just a couple of days after, we didn't yet know when exactly the tsunami had happened. But later, from type gauge data and so on, we got a rough estimate, even though the spatial or temporal sampling wasn't so great. But we started looking for potential candidates of what could it be. And while we were doing that, or colleagues were doing that, we found more evidence of tsunami runnouts. This is a satellite image. Previously, we were here at LAÖ at this island. Now we're a bit further into the fjord system. We're a bit further into the fjord systems, like 80 kilometers from here to here. And here you have a satellite image on the 14th of September, and then 1 day after the event had occurred. And you can see the change in the color of the ground, which is again, just like before in the photograph, an image of the tsunami runoff, of the water running up the slope of the sides here. And this went up laterally 500 meters, half a kilometer, much further than what we saw 80 kilometers east at LAÖ. So we knew we were getting closer to what caused this. And at that time, also in local media, You may not believe it, but there is local Eastern Greenland or Greenland media. They started reporting on this potential tsunami. From these satellite images, it's often easy to miss how amazing this landscape really is. This is a panorama picture of the same landscape instead of a satellite view here. And in the red line, you see roughly by hand drawn in where this 500-meter inwards line is, how far the water from its usual level went up on land. So we were getting closer, but we weren't quite there yet, because this was just further evidence of a tsunami. We hadn't found the cause yet. And then we found this region here. We're close to the tsunami radar that we saw earlier in this arm of the fjord. Now we're a bit further north in the side arm. This is called the Dixon Fjord. That is then our story all about. And this is a satellite image before the 16th of September. And then it will now change back and forth after the 16th of September, like a day later, the second picture is taken. And the color changes a bit, which is a bit unfortunate, but you can clearly see that in this region here, it changes dramatically what this looks like. And what you're looking at is a glacier starting from high up the mountains, down this gully into the Dixon Fjord. So here we're at the southern flank of the fjord. The glacier terminates into the fjord. And on the day later, it's all a big mess here. And something had happened, something massive had happened here that impacted this glacier. And you also see that in both images, the lighting conditions are roughly the same. You have sun towards the south. And then you see, for example, in both images that this part of the slope is bright and all of this is in the shade. And if you focus on this part here, that is all lit up because it is a mountaintop. In the second picture, it's gone. And you can see the light shining through like a small crack and then illuminating after this. This glacier here is exactly the one, just have to wait a second for this animation to finish, is exactly the one of this footage. Here we are now in Dixon Fjord, flying with a drone towards the glacier, up the glacier a little bit. And this footage was taken by the Joint Arctic Command. This is with partners together, the Danish military. They also noticed this event and were also curious what the hell it was. So they went 2 days after the event, or 3 days after the event. They went there, they sailed there and investigated what the hell had happened. And they took a drone and flew over it. And if you look at this glacier here, you see how dirty it is. There's so much rubble and dust and boulders on it because this is in the aftermath of the rock slide. In a second, I will show you something that makes it easier to get a sense of scale here, but it's really easy to lose the sense of scale. Like this dirty line here is roughly 100 meters high. So this is truly massive, and you really, if you just look at these images, you have no understanding of how big this stuff really is. But what is our main interest, at least at this point, is right up here, the mountaintop that is apparently missing. And this is 2-3 days after, and roughly a month before that, there was like a cruise in that same fjord, and they took a picture on the 12th of August. And for your convenience, it's now marked what will be the future rock slide, the mountaintop that is missing today. You also may notice that the glacier looks very much different. It's much higher compared to previously, and it looks much more, I understand that the picture is a bit low resolution, but it's much closer to what one would maybe usually expect a glacier to look like. And if we now make a comparison, although the point of view is not exactly the same, but we tried our best to overlay the two, you see the mountaintop before and after, and it's just simply missing. The same that we saw in the satellite images, this part of the mountaintop went missing. So now we knew there had been a massive rock slide in the vicinity of our seismic location that is the cause of the tsunami reports and the satellite images and the run-up measurements that we see. So how does this create a monochromatic seismic signal? And we think the full story of this goes like this. It starts with climate change. Permafrost thawing and glacier melting causes this slope, at least it's reasonable to assume that, causes this slope to destabilize. And for this specific glacier, the colors indicate how much elevation the glacier lost over the past few decades. This specific glacier lost its most amount of volume just right underneath where the landslide or the rock slide then ultimately went crashing down. It crashed, or it went down, right? Again, it's easy to lose the sense of scale here, but a massive volume. It was truly a massive rock slide. It's not the biggest rock slide there ever was, but it's really among the top rock slides with 25 million cubic meters. The colors indicate, so this is estimated from satellite images, and the colors indicate how much elevation was lost, and more than 200 meters in large parts of this mountaintop went down. The mass is roughly equivalent to 5,500 Eiffel Towers. We were struggling to get a comparative unit, something to think of this. It's really beyond what is easily imaginable for us, but 5,500 Eiffel Towers for sure is a lot. And this is the material that went down in this rock slide. So the rock slide happened, the slope destabilized, the material crashed onto the glacier. It entrained material off the glacier, and then a rock ice avalanche went down the glacier gully, crashing into the Dixon Fjord. This causes the tsunami that we see. A massive volume crashing into the fjord because it's now missing from the mountaintop. And on this figure, there are two lines indicated. One is called backsplash, 200 meters high, roughly. This is when the material crashed into the fjord, the initial backsplash of the water. And then there's a second line that is much dirtier. This is when the tsunami then developed in the fjord, went to the other side, reflected from the other fjord wall, came back, and then it went still up 60 meters in that part, 110 meters up here. This is now different from the 500 meters that we saw before. This was like lateral extent of the run-up. Here it is really vertical extent, 100 meters, 200 meters high, right next to this rock slide. And if you map it in the entire region, what members of our team have done, looked at satellite images. We started here at LAÖ, where the run-up indicated by the color is just a few meters. Then you saw here where it was 500 meters inland, but you already saw from the panoramic picture that it's not so steep topography. Here went up maybe 10 meters or so. And then here in the Dixon Fjord, you can really see several points where it's 60 meters and more, up to 200 meters, even for the run-up, not just for the backsplash. So we were happy in the sense that we knew there was a rock slide actually at the same time that our seismic signal set on. The same time our 92-second period signal started ringing the earth, we had this rock slide. And I'm skipping over all the rock slide stuff. People looked into modeling the rock slide itself, inverting the source position, and we were quite happy with this. If you look at higher frequencies, you can actually very well constrain the rock slide, even with just a handful of stations in the region. But what tsunami generated by rock slides certainly are not known for are monochromatic nature. Tsunamis are by nature very chaotic events that seismically speaking, you would expect to have a very broadband excitation of energy. And tsunamis are also not known to last for 9 days. Tsunamis are transient events. They go over once and then they're done. What we see in our seismic data goes for 9 days. So we had to find an explanation for that. And there was a lot of discussions going on, and it actually was a hypothesis that came up quite early. Because if you take the geometry of Dixon Fjord and you just take this part here, and you say, okay, this is like roughly 2 by 10 kilometers, and you assume something about its physical properties, and then you say, okay, what if this was a cylinder that I start ringing? What is its eigenfrequency? And it turns out that you're actually quite close to the 92 seconds. So we thought, okay, maybe this tsunami somehow caused the fjord to ring for 9 days. But there were all these problems that I had just mentioned. The way we approached this, and this was mainly led by the group in Paris, is to model the tsunami and see what happens. This is, again, a slightly different projection. This is a problem when you work in this area because it's so far up north. All the different projections look very different on the map. Now LAÖ is like up here, and this is the fjord system. Here we looked at the satellite image, and this is the Dixon Fjord. And what you will see in a second is the tsunami simulation with the colors indicating the water height, and then just over time generated by the rock slide. So it starts, and then you see the complex wave propagation through the entire fjord system. It reaches up here at LAÖ after 15 minutes or so. So the time is step up there, the timing there is in seconds. And the energy dissipates in a quite complex manner quite quickly. Except if you look very closely, except right here in Dixon Fjord itself. While all energy goes down, amplitudes go down, it seems that here waves are kind of trapped. And they're flipping back and forth, back and forth, back and forth. Right? The temporal resolution is not so great, but this was, right? So we were really running, or the colleagues were running simulations that were really at the edge of what tsunami modeling people are used to running in terms of temporal resolution, length of the simulation, spatial resolution, and so on. If we take two snapshots and zoom them in a little bit, just right after another, you see on this snapshot higher water heights towards the north, lower towards the south, and then it flips back. And then it just goes back and forth, back and forth, back and forth. So what we're seeing here is like a standing wave in the fjord, where the amplitudes are high on one side, and then they go like this, back and forth, back and forth. Standing wave in the fjord system comes out of the tsunami simulation. And we were really happy that this comes out of the tsunami simulation, because it was our main hypothesis that somehow that somehow there is a resonant process going on, which in this case is the standing wave, and it can explain a few of our observations. It explains the frequency, roughly, you will see in a second. We're in the right ballpark of this standing wave going up and down. And it can explain something that I have not mentioned yet at all. It can explain the radiation pattern of seismic waves. These are seismograms recorded at BFO in southern Germany. The one that Rudi noticed, just a bit more prepared so they don't look so weird. I mean, they still look pretty weird for a seismologist. But here you have the vertical component, radial and transverse component. That means at BFO, we have recorded more radial energy than transverse energy. There's more Rayleigh wave energy than Love wave energy in southern Germany. And if you take this ratio between the two and you map it worldwide, you get a distinct pattern, the radiation pattern of this source, where the green stations are stations where the Rayleigh waves are stronger and the Love waves are weaker. And the purplish purplish stations are stations where the Love waves are stronger. We call this Rayleigh node because it's the absence of Rayleigh waves. This has led to some confusion among ourselves as well, but this is what was agreed on, right? So Love waves along this line for all the purplish stations dominate, and for all the green ones, including BFO in southern Germany, Rayleigh waves dominate. And these two lines we had not estimated from this radiation pattern, but instead these two lines are the geometry of Dixon Fjord. The same two lines now mapping through Dixon Fjord. And then the explanation for the mechanism is that the standing wave, whenever it pushes on both sides of the fjord walls, and then you can model it as a single force pushing, alternating in both directions. when it pushes in that direction, you produce more Rayleigh waves in that direction and love waves perpendicular to it. And this we see in the seismic data. So we were happy. Yeah, we were happy. We can produce, again, show in a second, roughly the right frequency, and we can produce the radiation pattern, and it just comes naturally out of our simulation without enforcing that it must end up in a standing wave in any way. But there was a big problem. The big problem is that our seismic observations lasted for 9 days, and that our numerical simulation run lasted for 10 hours. The tsunami and the standing wave should dissipate after 10 hours, not 9 days. Right? This is a problem. But in any case, here now I have shown the frequency. And so out of the simulation, we get 12.4 millihertz. We observe 10.8. It's not exactly the same, but it's pretty good. For all intents and purposes, it's pretty good. The main problem is we lose energy much quicker in the simulation than we see in the seismic data. So while theories came up, how can we explain that energy dissipates this slowly? We weren't aware of any natural process that actually dissipates this slowly. And ideas came up. One wild idea, for example, was that whenever the standing wave is up on the southern side, it lifts up the glacier tongue, and then there's a subglacial lake underneath, and then water comes rushing down, and then you get energy influx in phase, which is one of the conditions that we had to meet, in phase with the existing motion, right? No one was really convinced by this, yeah? But this was discussed, and it ended up in the initial draft because we did not have an explanation for this. We did not know. But in any case, we submitted this with this problem because we didn't know how to solve it. We wrote down a few ideas. It could be this, it could be this, it could be this, why it doesn't match. But we just didn't know. And we felt that the observation itself is already enough to get recognition and be exciting. So just, or not even 4 months after the event started, we had the paper done and submitted, also with the 68 co-authors. So this was quite an undertaking to get it done this quickly. And we did submit it to Science as well. And a few months later, they rejected it.
A few months?
Yeah.
60 days, 2 months. Okay. That sucks.
Yeah, they rejected it. It went to the reviewers. The reviewers were very happy and, oh, this is exciting and everything, but this is not enough. This is not convincing enough. They rejected it exactly for this reason. Right? Out of the 3 reviewers, 1 had a problem, and then the editor decided to take on that problem as well. And this was the problem. Amplitude decayed too fast. And we did not have a sufficient convincing explanation for publication. But they opened up us the possibility of resubmission. So if we can figure it out, we get to go again. And then we figured it out. And what changed, and really the only thing that changed, is that while all this process was going on, Christian Svenevich, our lead author, was in close contact with the Danish military the entire time. They wanted to know what we had been doing, and we were happy to share what we had been doing. They were less happy to share what they had been doing. We don't know. Yeah. But they somehow in these discussions, I don't know how that went, somehow in these discussions, Christian convinced the Danish military to release the confidential bathymetry of the Dixon fjord system for us to use. So previously we relied on a elevation model based on publicly available data. And it seems that militaries have much higher precision bathymetry data all around the world, I assume, including in this very remote fjord. And they were happy to to share it with us, and they allowed us to use it and also to publish it together with the paper. So we were super happy about that. And then the colleagues from Paris said, okay, give us the new model, we go again. And this is almost the only thing they changed. And then the amplitude decay fits. What? Then you actually get the right amplitude decay. You need the better model, and what they changed is that they went to a very high spatial resolution. 3 meters was this model run, much, much, much higher than tsunami modeling people usually do. This was a simulation run that ran like for 3 weeks or something on the Paris cluster to get this done. They did some limit tests, like what happens if we go further and so on. And it turns out that the decay of the standing wave is really just a numerical inaccuracy problem, numerical loss of energy. It's not real loss of energy. And we move closer to the right frequency. Previously, it was at 12.4 hertz. Now it's 11.4. Still not perfectly, but pretty good. I would say pretty good. Yeah. So we resubmitted. This is really the only thing that changed from between January 9th when we first submitted and then rejected March 9th. And then half a year later, September 12th, almost to the day, almost on the event's birthday, we got this paper published. And we were super happy. Of course, in science it's always great, but the story was really a lot of fun and really great. And science warned us before we published this, that this will likely gain more media attention than is usual. For a paper, for sure, but also for science papers. They expected more media requests and so on. Get ready for that. And they had a whole strategy, and there were national media coordinators and all of this stuff. A whole thing. And they were right. This was picked up worldwide by all the media. We had articles in print, in online, The Guardian, BBC, Spiegel, all kinds of media. People were on TV. This is Vita on the Belgian TV. This is Rudi, the guy that saw it in the Black Forest, explaining the standing wave in like a drain pipe. And it's a great, I can post that maybe somewhere. It's a great video. He explained it really well. This is Stephen at BBC News Radio, and there was a lot of media attention and a lot of media buzz. It also created some creativity from others. I really like this animation that was part of one publication of the gong hitting the earth right in eastern Greenland. And we also got our own comic, little cartoon. This is also in The Guardian. And I guess these figures in the lab coats, this is us. But it was really a very eventful time, but quite exciting, of course. And we thought, that was it. Yeah? This went for maybe a week, this media frenzy. I'm luckily, in a way, I guess, far enough down the author list that all the top authors, they were approached much more than I was. So I wasn't part of that. But after a week or so, it went quiet. There were already, while this stuff was in review, some chats here and there. Oh, what could we do next? What a follow-up study could be? Because as any nice research, this opened up more questions than it answered. There's a whole bunch of stuff left to do. But for a while, everybody was done with it. And then a month later, after we published, Mattermost, our chat picked up again, because Christian, lead author, posted this message. Holy Mother of Sage, I was just contacted by a Danish student who's taking a cryosphere course and what he looked at was satellite data of the IceSat-2, the satellite designed to measure profiles of ice elevation. And in this cryosphere course, I believe it's a master student, the instructors told him, yeah, you just look at some data and whatever you find interesting, have a go. This student heard about our paper and he thought, what happens if I look at a profile crossing the Dixon Fjord? Because as it happens, and we had no idea, as it happens, the satellite, I believe on the day after the onset of the event, flew right over Dixon Fjord and measured a profile of elevation. And it's designed to measure ice elevation, but apparently it also measures water elevation. So this is just a profile through crossing Dixon Fjord along this line. It's a snapshot of the standing wave. We thought there was no direct observation of the standing wave. We thought there was no way in hell that there is a direct observation of this, but it turns out there is. So this is quite exciting, but it doesn't stop there. About a month later, there popped up a preprint on arXiv, first observations of the sage that shook the world. Yeah, what a fantastic paper title. And this is their main figure. And what you see here is from a new satellite that was launched a few years ago, SWOT, S-W-O-T. It's a surface water and ocean topography satellite that is designed to measure water elevation. And it apparently takes a bit of data massaging and a bit of processing to get nice images out of this. But they got this image out of this, where again, the colors are water elevation. In this snapshot, down here, further up than usual or the mean, and in the north, further down. They also draw these lines here are our Love and Rayleigh notes that they also have in their paper. And this was really exciting because not just like qualitatively this fits really well. This is the numerical simulation, different color scale and everything, yes. But it's also plus minus 1 meter, different time, different times of the simulation run and of this measurement. But you see these two areas of stronger elevation. You see them here. These are the same two. You see this blob here. It's this blob here. It really fits exceptionally well. And we were super pleased to see this, that our hypothesis was not just because it was entirely based on inference from seismic data, from the numerical, from the tsunami simulation and so on. And here now, in the last few months, there are actually results showing direct observations of it. So that brings me to the end, in question marks, today. There are more things to do. I just mentioned some questions popped up. I think the main question that I personally have is, why is this the first time we see this kind of signal if it's just a natural process? Is Dixon Fjord really the only fjord in the entire world that can produce a standing wave that is this stable? If yes, what is so special about Dixon Fjord? Many questions about this, and there's some work starting now. People get motivated again to start working on these kinds of related topics. I can tell you that it's not the only event of this kind. Once you know what to look for, it's easy to find more. There are 3 more examples. This is a month later, the same mountain slope, the same glacier gully, another rock slide happened. We have satellite images of that again, crashing into the same fjord, and we see the same kind of signal lasting several days again. But we also see it in 2017. Of course, it's much weaker. In 2016, again, shorter and weaker. And there are more examples also from 2006 and 2007. And at least for one of them, we also have confirmation by satellite images that there was a rock slide at the same time in the same glacier gully of the same mountain top. So once you know what to look for, there are more. There are 5, 6, including the one I talked about today, that we know of, but maybe there's more. And maybe there are more fjords to look for. And if you find this kind of stuff interesting, come chat to me. There's a few questions that could be approached by a master's project if you're still looking for one and you think this is a good topic. One final thing before I leave you. To get really in the Christmas mood, we thought it would be a fun idea to watch a disaster movie here in 2 days. Right here, we will watch The Wave. And we watch it because it's very on topic. It's a disaster movie about a rock slide generated tsunami into a fjord. Not in Greenland, but in Norway. But it fits so well. We thought, okay, we have to go with this. So on Wednesday at 4 here in the room, if you want to join, you're more than welcome to. We will watch this together. Yeah, and that brings me to the end. For me personally, it was really a unique experience. I believe this kind of frenzy. It's not something that is sustainable. I noticed this after the winter term. That was quite a lot. But it was really an exciting opportunity. Got to meet many people, worked on very interesting things. And with that, I thank you very much.